Welcome back to another explainer. Okay, let's jump right into this, because today we are tackling an absolutely massive mathematical mountain. We're going on a journey that starts deep in the abstract, highly technical realm of pure operator algebra, and we are going to climb all the way to the awe-inspiring physics of black hole thermodynamics and the structure of space-time itself. I know, it sounds like pure science fiction, but this is grounded in incredibly rigorous mathematics. We're going to explore how the Adelic Langlands program might just be the ultimate key to proving a notoriously stubborn open problem, Crouzeix's conjecture. Let's get started.
Here is our roadmap for today. We'll start with the matrix amplification limit, then move into the Adelic nilpotent collapse and map the dual group. After that, we'll dive into the Koszul boundary complex, transition into holographic thermodynamics, and finally tie it all together with automorphic cosmological balance.
Starting off with Section 1, the matrix amplification limit and the classical ceiling. At the heart of all this is Crouzeix's conjecture. It fundamentally states that for any square matrix or bounded linear operator A, the operator norm of a polynomial of A is strictly bounded by a specific constant multiplied by the maximum absolute value of that polynomial on its numerical range. If we trace the history of this constant, it's pretty wild. Back in 2007, Michel Crouzeix proved this inequality held for a constant of 11.08. By 2017, mathematicians managed to squeeze that down to about 2.41. But the holy grail, the absolute theoretical maximum limit of operator amplification, the conjecture says it's exactly 2.0.
So you might be wondering, why is hitting exactly 2.0 so insanely difficult in classical math? Well, classical analysis operates in the Archimedean continuum, your standard real and complex numbers. And honestly, it's kind of like the Wild West. Geometric boundaries there are chaotic, fractal, and highly irregular. That chaos causes phase misalignments, which is exactly what creates those loose bounds like 2.41. But the Adelic strategy takes a totally different route. It uses non-Archimedean, p-adic sectors. Think of these discrete fractions over a Brouhat-Tits tree as a natural geometric filter. The strong triangle inequality acts like a mathematical bouncer, ruthlessly clamping down on those errors and forcing all that chaos into a rigid, minimal 2x2 symmetric grid.
Moving right along to Section 2, the Adelic nilpotent collapse strategy. Think of this strategy as our escape route from classical chaos. We don't just stare at an isolated matrix and hope for the best. Step by step, we systematically map our bounded operator using a Dirac operator into an infinite-dimensional Adelic automorphic Hilbert space. From there, we extract the Satake parameters, which forces our highly ramified spectral boundary to lift all the way up into the Langlands dual group. Finally, global functional equation integration triggers what we call a regular nilpotent collapse, systematically crushing our constant down to exactly 2.0. Let's actually break down the math making this happen. This brings us to the Kahn-Shamsuddin spectral action formula. We're evaluating the operator norm as a global trace over the Adel ring. Notice how the global trace factors beautifully into two really distinct parts. First, you have the continuous Archimedean component. This is where all those non-local quantum correlations seem to just wildly fluctuate. But crucially, it's multiplied by the discrete p-adic components. These act as vital multiplicative filters that systematically dampen and smooth out the off-diagonal phase errors.
Section 3, mapping the dual group, also known as the Satake collapse. The linchpin here is the commutation restriction. We are essentially forcing the commutator of our local operator and our regular nilpotent operator E to equal 0. When we map our polynomial chains to the Langlands dual group, they manifest as this operator E. Now, for the whole system to remain stable under the global functional equation, the local Satake matrices absolutely must commute perfectly with E. The result? A Satake eigenvalue collapse. All those messy, non-diagonal, infinite degrees of freedom just vanish. The internal algebraic dimensions are entirely eradicated, condensing everything onto a beautifully uniform degenerate diagonal matrix.
Section 4, the Koszul boundary complex and how we mathematically force this limit.
To actually pull this off, we have to bring in a very specific homological tool, Koszul homology. Basically, this lets us evaluate exactly how a polynomial operator interacts with the geometric boundary of its numerical range by treating it as an intersecting chain complex. It's brilliant because it allows us to track the boundary configuration purely algebraically, without getting lost in the geometry.
We start by setting up a sequence of boundary proximity operators, those delta terms, which measure the normal distance from the operator to the tangent planes of the boundary. But the real magic happens with the boundary differential operator. By passing these Koszul modules through a Grothendieck-Riemann-Roch push-forward, You can visualize this as a massive mathematical funnel. This differential operator maps directly onto that regular nilpotent orbit we just talked about in the Langlands dual group.
Because that regular nilpotent operator completely restricts the higher-order Koszul modules, they vanish everywhere except at a single, stable, two-dimensional boundary. In our final limit equation, the operator trace limit collapses directly onto the logarithmic derivative of the zeta function, which rigorously and inevitably outputs our constant of 2. It mathematically proves that the absolute maximum amplification of a matrix operator is strictly a two-dimensional phenomenon. You get exactly 2.0. No more, no less.
Section 5, Holographic Thermodynamics. This is the physical paradigm shift.
All right, we have conquered the pure math. But honestly, this is where things get truly mind-blowing. Let's completely shift our mental model. That mathematical matrix operator, isn't just numbers on a whiteboard anymore. In Lagos field theory, it represents a localized quantum field distortion, literally a wave packet passing through curved spacetime. And that rigid Crouzeix constant of exactly 2.0, that is the absolute upper bound on its physical wave dispersion. The quantum vacuum is mathematically prevented from tearing itself apart because the maximum amplification of a quantum wave packet simply cannot exceed twice its input energy.
The absolute upper bound on physical wave dispersion. Just think about the profound weight of that idea for a second. The universe fundamentally shapes its own continuous macroscopic dimensions to ensure that the cross-entropy of its fields remains perfectly minimized. It is literally using pure number theory as a physical governor for reality.
To actually prove this link to thermodynamics, we construct an active density state, representing highly entangled quantum horizon correlations. When we calculate the maximum informational divergence, that mathematical constant of 2.0, squared to 4, translates geometrically into an explicit, unyielding logarithmic information penalty.
And that brings us to the massive holographic relative entropy identity. This perfectly maps our mathematical bound straight onto the relative entropy limits of a black hole horizon. You'll notice the exact natural log of 2.0 term acting as a multiplier. We call this the quantized entanglement bound, and it acts as a literal cosmic censorship mechanism. If a quantum state could somehow bypass that 2.0 bound, the entropy would overflow, the black hole area would shrink, and it would create an unstable naked singularity. In astrophysics, that is essentially a cosmic doomsday scenario, but the math strictly forbids it.
Finally, Section 6, Automorphic Cosmological Balance and the Non-Abelian Network. Instead of just looking at a single isolated channel, what if we bundle competing operators into a non-abelian GL2A field vector? Our Satake matrix evolves into a rank 2 diagonal matrix tracking the dual eigenvalues of our competing fields. The non-abelian Crouzeix bound dictates that the absolute maximum difference between these eigenvalues cannot exceed 2. This is known as the Hecke-Moss stability criteria. It strictly clamps the phase divergence between intertwined fields, meaning they are mathematically forbidden from oscillating chaotically and destabilizing spacetime.
To globally enforce that stability, our relative entropy functional actually absorbs the logarithmic derivative of the degree 2 cuspidal automorphic L function. This is self-regulation via Langlands functoriality. If one field spikes in entropy, the non-abelian coupling literally forces the competing field to adjust symmetrically. It maintains perfect reflection symmetry and absolutely prevents any local informational anomalies.
So bringing all these threads together, we're looking at an absolute unyielding harmony. The mathematics forces chaotic matrix dimensions to collapse into minimal 2x2 unramified Jordan blocks. The information theory bounds local entropy mathematically, acting as that vital cosmic censorship mechanism. And the physics reveals spacetime itself as a perfectly self-contained, closed information mesh, where continuous macroscopic horizons and discrete p-adic trees work together to keep global cross-entropy perfectly minimized.
Which leaves us with a pretty incredible final thought for today's explainer. If the universe literally limits its own mathematical boundaries just to protect the stability of the physical vacuum, what other fundamental physical laws are hiding right now, just waiting to be discovered, deep in the realms of pure number theory? It's a lot to think about. Keep exploring, and thanks so much for joining me today.